So previously we defined the clique tree algorithm, which is just the belief propagation algorithm run over a graph that happens to be a tree. As it turns out, we can exploit the aspects of the tree to greatly improve the computational behavior of this algorithm, not just its correctness, which is what we showed before. So let's go back to our message passing in this very simple tree, which has just these 4 clusters, A, B, B, C, C, D, and D, E. And let's see what the messages do. So here is the message delta 1, 2, which is the message that's passed on this edge. And here's the message delta 2, 3, and so on. And these are the 6 messages that we have. And now we can notice one very important property. Delta 1, 2, once computed, never changes. So you get instant convergence of delta 1, 2. Once you compute it for the very first time, you're at convergence. Now what about delta 2, 3? Well, that depends on when delta 2, 3 is passed. If delta 2, 3 is passed first, before cluster 2 gets a message from cluster 1, then once it gets that message, things might change. But if cluster 2 is clever, it's going to wait. And it waits until that message is passed. And once that message is passed, since it doesn't change, delta 2, 3 doesn't change either, ever, if it's smart enough to wait. What about delta 3, 4? Delta 3, 4 needs to wait a little bit longer because it needs to wait for delta 2, 3. But if it waits for both delta 1, 2 to be passed to cluster 2 and delta 2, 3 to be passed to cluster 3, then now that it sends delta 3, 4, delta 3, 4 doesn't change either. So delta 2, 3 has to wait for delta 1, 2. And delta 3, 4 has to wait for delta 2, 3. But assuming it waits, then convergence is achieved in a single message passing step. Now, there's nothing magical about going left to right. If you go right to left, you get the exact same behavior. So here you have that this one converges instantly. This one, you need to wait for delta 4, 3. And this one you need to wait for delta 3, 2. But again, assuming you wait, then the messages converge in a single step. And so we can compute all of the messages in this entire tree in one pass in either direction. One pass from left to right and one pass from right to left. In the context of chain structures like this one, this actually has its own name. So for chains, you might see this under the name forward-backward algorithm. And it's very commonly used in things like hidden Markov models and other similar chain-structured representations. And so the point is, the total effort that we had to compute all of these messages is just one message passing step in each direction. One from left to right and one from right to left. And the result of that, remember that once all messages have been passed, we have beliefs that are correct, beliefs that represent, that are marginals of p tilde phi. And so we've computed all of the marginals of all of the clusters in this graph in sort of 2 sweeps over this clique tree. And so more generally, as we said, one CI receives a final message from all of its neighbors except for CJ. If it waits to send the message to J until it receives a message from everybody else, then that message, delta ij, is also final. So if these are final, this is also final. Can you always find a message passing order that will achieve that goal? I mean, maybe everybody ends up waiting for everybody else and they all get stuck and they never send anybody any messages. The point is that you could always start, because the message from a leaf is always immediately final. And once the message from a leaf is finalized, then you can send the message from the parents of the leaf, and so on and so forth. And because this is a tree, it's guaranteed that you will be able to find a legal message passing order. And if we pass the messages in the right order, then we only need to pass 2k minus 1 messages, where k is the total number of clusters. And why is that? Because if you have a tree over k nodes, in this case k clusters, then there's k minus 1 edges. And since each edge has a message in both directions, so we have k minus 1 k minus 1 edges, and therefore 2 k minus 1 messages, one in each direction. Let's look at a couple of message passing orders to see which ones are going to work and which ones aren't. So we can start with any leaf works. So say we start with, C2. Once C2 has passed its message, what other clique can pass its message? Well, C3 can't pass messages yet, because it's still waiting for messages from all sorts of other guys. So we have to go to another leaf. For example, C1. C1 can pass a message now. Neither C3 nor C4 are candidates for message passing yet, because each of them is still waiting for another message. But C6 can pass a message, and now we have the option of activating C4. C4 can now send the message to C3, because it got everything except the message from C3 before. C7 can say pass a message to C3, and you notice there is a lot of arbitrary decisions on how I ordered this. I could have used C5 next. And now C3 has the option of passing a message to C5. And notice that at this point, everyone has received all of the messages, or all of the messages but one. And so now we can start passing in the other direction. So C5 can pass a message to C3. C3 can pass a message to any of C2, C7, or C4. And at this point, C4 can pass a message to both C6 and C1. What is an example of an illegal message passing order? So for example, if C1 passes a message to C4 and C4 jumps the gun and says, yay, I'm going to send the message to C3 next, that is an illegal message passing order, because C4 does not yet have all the information that it needs to pass a message to C3. It's still waiting for a message from C6. So that's not a good ordering. Clique trees have other very elegant computational properties that make them a useful data structure. So let's think about the kinds of queries that one can answer using clique trees, and some of these are fairly obvious, but others are a little bit more subtle. So imagine that we wanted to answer a posterior distribution query on either a single variable or a set of variables that appear together in a clique. Well, in this case, you could take any clique that contains all of those variables and sum out the variables that you don't care about from that clique to get a posterior over just those variables. Now remember that that posterior is p tilde phi. It's an unnormalized measure. So in order to get the normalized measure, you actually need to renormalize. Now, you could also do something a little bit more clever. You could say you wanted to introduce new evidence regarding some variable and query another variable. So this is a form of incremental inference, where you've already calibrated the clique tree, and now you say, ooh, wait a minute, I made another observation. Let's see what happens now. So it turns out the clique trees are really good for that. And so we're going to divide this into two cases, the easy case and the slightly less easy case. So imagine that we want to query a variable x that appears in the clique with my new evidence z. So here is my clique, and here is z, and here is x, and I'm going to, and I want to figure out what the posterior of x would be if I further observe z. Well, this is actually really easy, because what I have here is p tilde phi of, let's assume for the moment, just z and x. If there's other variables there, it doesn't change anything, because we could always just get rid of them. We can now condition or reduce the clique. So this is a clique reduction by just restricting attention to the entries that are consistent with my evidence z. And then I end up with p tilde phi of little z comma x. And in order to get a posterior, I can sum out the relevant variables and renormalize. I can do incremental inference. Okay, well, that's the easy case if the two variables are together in a clique. What about a somewhat more elaborate case where I introduce the new evidence and I query a variable that doesn't appear in the same variable, in the same clique as z? So using an example, let's imagine that what I did is observe evidence on A, and I want to query, say, E. Actually, let's do a different example. Let's imagine that I want to query D. Well, in this case, I can do the following. I can multiply this indicator function, or what we call this reduction of the factor, into a cluster that contains the evidence. So in this case, we're going to multiply in the indicator function of A equals little a, which corresponds to removing all entries in cluster 1, in the beliefs of cluster 1 that are not consistent with sorry, not into the beliefs. We multiply it into psi 1, removing all entries that are inconsistent with that. So now, what happens when we change psi 1? Imagine that we were doing this entire computation from scratch. That is, forget everything that we did before and think what would happen to this model in the hypothetical case that we were passing messages with a new psi 1 instead of the old psi 1. Well, some messages would change. Which messages would change? Delta 1, 2 would change because psi 1 changed. Delta 2, 3 would change because delta 1, 2 changed. Delta 3, 4 would change, but we don't care about delta 3, 4 if we're interested in this belief over here. What about other messages? Delta 4, 3 doesn't change. Neither does delta 3, 2. Neither does delta 2, 1. And so only a subset of the messages in the clique tree change as a result of this change, which means that we can reuse at least half the messages, if not more, in computing our beliefs about, in this case, cluster 3. And the only messages that we need to recompute are the messages that are along the path to a clique that contains the variable x that we want to query, which in this case is cluster 3. So to summarize, if we have a clique tree with k cliques, and we pass messages in a careful order, which means that we start at the leaves and propagate inwards, then we can construct an ordering such that 2k minus 1 messages suffice to compute all of the beliefs in the clique tree, which means we get a posterior over every single variable in the model. Contrast that with the computational cost of running variable elimination n times to compute posteriors in n different variables. Here, you get a considerable computational savings, in fact, a computational savings of order of the number of variables. And so what we can do is we can compute all of the marginals at only twice the cost of variable elimination as opposed to n times the cost of variable elimination. And we've also shown that by caching or storing the messages, we can reuse inference, for example, in the context of incremental queries, which provides us with a useful data structure to keep updating as we obtain additional evidence.